Okay, it's 17th of March. Nice Bhubaneswar. Bhagirathi 127. It's almost been 12 hours since my last session. This is session 3 to understand condensed matter physics. Okay, primary source would be lecture notes by David Tong. And yeah, I just woke up and I just need to get warmed up. I'll do a good recap of things as usual, and we'll start from there. So essentially this session will occupy applying tight binding model in order to see metal and insulators arising out of this theory, and then we'll look at this very interesting approximation called nearly free electrons, where you don't discretize the space but you perturb the free particle Hamiltonian by a periodic potential which mimics the lattice. Right. Cool. Right. The potential is periodic, but the space is not discrete anymore. Yep. But there's still a lattice, you see? There's still a lattice, like the fact that there's an atom. There's an atom in every lattice. That's still there. Now you allow the electron to wander between the lattice sites. So that's the nearly free electron, where there's a lot of perturbation theory to be applied and understood, a lot of physics to be fleshed out, a lot of mathematics to get to set things, and lots of subtleties where I was stuck last time. This time I might be able to fix them, and you will get the band structure out of it in the end, and that should be pretty interesting. Let's see what I can do. Interesting stuff ahead, and I need to start a first look at metals and insulator. So last night, what have I done? Okay, so basically I've solved the tight binding model. Before this, in session 1, we saw the Hamiltonian form for Hamiltonian in the tight binding model. You had this beautiful Hamiltonian which allows hopping to its nearest, which allows electrons to hop to its nearest sites. You understood that Hamiltonian reasonably, and then you did this eigenvalue. You use this Schrodinger equation to get a linear equation in psi n minus 1, psi n plus 1, which then you use the ansatz of I e exponential I k n a. You saw some things, you described k, you saw that k belongs to some domain, or else it just repeats, solutions just repeat. There's no use with that. So you restrict k to a Brillouin zone, a zone called Brillouin zone, minus pi by a to pi plus pi by a, pi by not included, minus pi by included, and that's the Brillouin zone, and k is discretized, as said, periodic x implied, k is discretized. But here is also true that you have discretized x, and so k was periodic, right? This Brillouin zone implies that k is actually periodic. Cool. So okay, and there is some subtlety in this discreteness of k, which I remember Tong kind of doesn't mention it after this discussion. He doesn't mention it anywhere, right? He uses it He doesn't care about it. So what I think is that, yeah, so it's a finer discreteness than the Brillouin zone, gaps boundaries itself. So it can be a fair argument, but we'll be analytical about it. We'll be carefully analyzing that stuff when the time comes. And so we use the ansatz, and the linear equation now tells us the energy in function of the hopping parameter T um, and the boarding energy E naught, just the free energy without the hopping and stuff. It's interesting to see what physically E naught is, right? Okay, what is E naught physically? Physically, what is E naught? Physically, what is E naught? E naught is basically the energy of each state under the boring Hamiltonian, where your things doesn't move at all. Your electrons are just fixed there. So it's kind of valence energy, right? It's kind of valence energy. It's kind of, yeah. T is very, very, very small. Let's say very small. Then E naught is essentially the energy that insulators or some kind of stuff have. But yeah, I think we can in turn understand more about E naught as well. As T tends to 0, you get E is E naught. So if you restrict the Hamiltonian, if you restrict the hopping, your energy is essentially E naught, or something like that. In fact, okay, yeah, or yeah, something like that. Okay, then we saw the small plot for some values of A and T and E naught in a Brillouin zone. Okay, so we saw the nearest neighbor interactions led to completely localized energy eigenstates. Okay. What? Okay. So okay. Instead, all energy eigenstates are spread throughout the whole lattice. Arbitrary. How do you know this point? Okay, this he just mentioned it. There is a lot of things to do for this, to reach at this point, right? Right? You need to see the bra x get m kind of thing. Psi and x take a product and you kind of get the wave function out of it, right? Delocalized energy states. That's not a straightforward statement to just put it right there. Anyway, the degeneracy is lifted by hopping parameter labeled by k. Really, you clearly see that negative case and positive case are the same thing, even in your energy thing. The fuck? Where did the degenerate got lifted, huh? Really, the energy states of H0 were completely degenerate. Adding the hopping term left this degeneracy. Really? What the fuck are you talking about? Instead, the eigenstates are labeled by wave vector k and energies that lie in a range. What? What? What the heck? Completely degenerate? Okay. Yeah. Oh man. My profanity went extreme there. But yeah, essentially. Yep, it did got lifted. I mean, initially it was just E0 for all the states, bruh. It got completely lifted and each state has a different thing, right? It's T-dependent thing and it's a K, labeled by K. Exactly, labeled by K and have energies that lie in this, with a bandwidth of this much and basically a band, right? Now for low momentum, your energy for low momentum, your energy is kind of E minus, it's just a constant term plus a free particle-ish term, okay? So free particle-ish term, yep. So yeah, free particle energy up to a constant period effective mass, which has nothing to do with the real mass of electron, nothing to do with physical mass. The physical mass of electrons. Okay. Anyway, yeah, there's a reciprocity between P and X. I mentioned that you apply periodic X, you get a discrete K. You apply a discrete X, you get a periodic K. Interesting. And he blows my mind saying, at last he says, in the last he mentions that more generally, discreteness is the Fourier transform of a compactness. Oh my god. Shit, bro. Okay. Okay. Discreteness is the Fourier transform of compactness. Compact space. Fourier transform of that space. Fourier space. I don't know. Where do you learn this all Fourier space? Harmonic analysis? Right? Fourier space. Where does one learn? Where does one learn about Fourier space? for transform and stuff, man. Okay, harmonic analysis. Is a Braxton that function and representation and frequency. Okay, L2 space. Functional analysis. Excuse me. Anyway, so that was a recap. That's a good recap of things. Yeah, the normalization of the answers kind of gives you that you just add 1 by root n to it, right? Normalized. Where did I say? Right, yeah. Normalized thing is cyan. If you want, if you are a normalized person, right? Make it an by root n. Okay, there's this drama thing going on. There's Trisha going on. But I want to sacrifice them. Okay. So that was a recap of things. Now let me mention some background thoughts of mine. So there's Tusha happening Mysore, the Inter College Fest. I participated in a 5K race in the spirit of participation. And I think there are cultural events starting today. I wish I could go to them, but I just want to sacrifice and learn. I really want to read this stuff It's not much of sacrifice, though. It's just not going. I mean, it's just I mean, it's not much. It doesn't. Yeah. As much as it sounds, doesn't. It's not as such a big sacrifice. Okay. So yeah. Anyway, we'll start with. Yep, I'll start applying the theory now. Okay, first look at metals on insulators. Okay, I won't put that heading. There's further physics to uncover if we consider more than one electron moving in the lattice. This section is just to give a flavor of these ideas. We will discuss them in more detail in section 3.1. This should be interesting. Section 3.1 में more details we'll find about multi-electrons and stuff. That should be very interesting. But, well, we'll give some flavor to it. Now, for simplicity, we'll assume that electrons do not interact with each other. No electron-electron interaction. Okay. Now, the states of the system is governed by Pauli's exclusion principle. Pauli exclusion principle. Okay. Exclusion principle. Two electrons are not allowed to occupy the same state. Yes, sir. Now, as you have seen, our tight binding model contains n states, right? However, each electron has two internal states. Tight binding model में there are n states, but each have a. This is possible. That's a fair degree of freedom for electrons. So this means that there are two n states, different states, right? Invoking the Pauli expression, we see that a tight bond makes sense as long as the number of electrons is less than or equal to 2n. So, yep, makes sense as long as there are less than or equal to 2n electrons in the system. In the repeating units of n, basically in this 2n electrons chilling here. Okay, so Pauli expression means that the ground state of multi-electron system has interesting properties. The first two electrons that we put in the system can both sit in lower energy with k equals 0 as long as they have opposite spins. The next electron that we put in finds this oxide occupied must sit in the next available energy state, which has k equals to plus or minus 2 pi n. Yes, sir. And also this continues with subsequent electrons sitting in the lowest energy states. And so this continues with subsequent electrons sitting in the lowest energy states. The net result is that electrons fill all the states up to final kf, which is known as the Fermi momentum. Okay. Electrons fill up to a certain kf known as Fermi momentum. Certain final kf, the boundary between the occupied and unoccupied states. Occupied, unoccupied is called Fermi surface. Well, note that it is a surface in momentum space rather than in real space. We'll describe this more detail in 3.1. Okay. how many electrons exist in real material? Here something nice happens. Because the electrons which are hopping around in lattice come from the electrons from the atoms themselves, one sometimes talks about each atom donating an electron. Following a chemistry, these are called valence electrons. Given that our lattice contains n atoms, it's most natural to talk about the situation where the system contains Zn electrons, where Z is the valency of atoms, atom and system. Zn number of electrons. Okay, the atom is said to have valency Z. Okay, suppose Z equals to n. For Z equals to n, we have n electrons, then only half of the state are filled with. Z equals to 1, we have n electrons. Half of the states are filled, and Kf is essentially pi by 2a, right? It starts at 0. Okay, Kf is 2 pi by a. So you put one here. Okay, Z equals to 1, there are n electrons. There are 2 in states. So half of them are filled. Basically 2 pi by Na m. There are n states basically. हाफ इसमें, so पाई बाय ए तक जाएगा. So if you go to n by 2, we'll have n states, right? If you just occupy n by 2. Really? Really? Yeah, when you mean by half, see. See, there are n electrons, right? Okay. First put one in ground state. 2 are done. 4 are done. 6 are done. So m equals to 0, m equals to 1, m equals to 2. How many m's do you need? So here 2 electrons are done. 6 electrons are done. 6, 9, 10 are done. Four. Each adds 4 next, right? Each adds 4. Right? So basically 4n plus 2. So 4 and minus 2 by 4. Really? That's so bad. It should be an integer though. So what the hell, man? Okay. So first thing is there are 2n states. Basically n, each 2. So how would you fill all this, right? 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Right? So moment 1 is occupied, 2 electrons are gone, 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 2 electrons are gone. This is stop sign, this is false. Okay. There are 2n, you stop at n. Yeah, n by 2, sorry. Each has covered n already. So you only need half of the states, right? States are filled. This is shown here. Note that there are so half of the states are filled. Okay, this is stating that there is no stress, and k plus number is equals to k minus number, which is a statement that no current in the ground state of the system. In the ground state of the system. Okay. Next thing, we can now ask, what are the low energy excitations of the system? We see that there are many. We can take any electron just below the Fermi surface and promote it to an electron just above the Fermi surface at a relatively small cost in energy. This becomes particularly relevant if we perturb the system slightly. For example, we could ask what happens if you apply an electric field. As we'll describe in more detail in 3.1, the ground state of a system rearranges itself at just a small cost of energy. Some left moving states below the Fermi surface become unoccupied, while right moving states above the Fermi surface become occupied, such that the number of electrons with k greater than 0, this results in an electric current. What we just have described is a conductor. Under low energy excitations, number of k plus will be greater than number of k minus, current exists. Electric current, say electric field, electric current, which describes a conductor. Two excitations are possible. But what about z equals to 2? This implies that there are 2 n electrons completely filled states. No excitations possible. No excited states. No excited states? What? No excited states, really? Now we don't get any choice to occupy states and since are occupied. Said another way, the multiparticle reverse phase contains a single state. Reverse phase contains just a single state. Multiparticle Hilbert space contains just a single state. Of course, you've neglected the interaction between them, and it's very it adds to probably very subtle theory. The fuck probably adds many subtle points. If you put up with an electric field, then electrons can't move anywhere simply because there's nowhere to go. They're blocked in place by the Pauli principle. This means that despite the presence of electric field, there is no electric current. This is what we call an insulator. So we have got an insulator here. It's sometimes said to be a band insulator to distinguish from insulators, other mechanics that lead to insulating behavior. And sometimes said to other mechanics that also lead to insulating behavior. Okay. Band insulator, insulating behavior. Sometimes said to be a band insulator, distinguished from other mechanisms that also lead to insulating behavior. The difference between a conductor and insulator is one of the most striking characterizations of materials that we all learned in high school. The rough sketches of above is telling that this distinction arises due to quantum phenomena, the formation of energy bands and the Pauli exclusion principle. I'll explore this more in section 3.1. Okay. A quick glimpse of conductors and insulators. Cool. There are many subtle points. Come on, if n is not even, how do you even define n by 2, right? What you know is there are 2n states. Like what they are in total an even number of states, okay? There are n. Only if n is even, right? Only if n is even, they are equal. Or else there is a one chain. There's one electron going that side, man. If n is not even, right? Okay, let's see. Let's conclude that. Okay. z equals to 1, we have n electrons, we have 2n states. What are these 2n states, right? K equals to 0. Okay, well, K equals to 0, spin up, spin down. K equals to minus pi by A, spin up, spin down. K equals to, no. And states, right? Basically into n by 2 into n by 2. Actually is not included, so only n states. नहीं है, 2 का n नहीं है, minus 1 है. That edge effects is always there. I hate to analyze this kind of stuff. But why don't they do it, man? Why do they just neglect it? Okay, anyway. Okay, and k is minus 2 by n a n by 2. So what is it? So you fill this, you fill this, you fill this. So what? How many states are done now? There are n states, remember? There are n kind of. If you just add these all states, n states. Right? Covered this, this, and this. You covered 3, 4, 5, 6, 7. 8, 9, 10. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Let's say 5 states are here. Let's say n by 2 is. Point 1 is that, What? Oopsie. Well, so if n is odd, then there's no way you can write n by 2, right? So you start with m equals to 1, m equals to 2, m equals to 3, and so on. Maybe m equals to n minus 1 by 2, m equals to minus 1, m equals to minus 2, and so on to m equals to minus of n minus 1 by 2, right? What if this happens? If this happens, then if you fill it up to minus 1 by 2 into 2, here also minus again n minus 1 by 2 into 2, and you just 1 into 2. If you add these, oh my god. अच्छा by 2 into 2 by 2 into 2, what happens? The consistency check n, okay, minus half, n plus 1, you get 1. So you got to reduce one more state here. 1 minus 2 by 2 may not be 8, right? So plus 1 state, so 1 state is extra, so there is a, so you got to remove, so you have to remove, so remove 1, okay, so you got to fill, so you got to fill one state with only one spin. So number of electrons balance will reduce, balances out, so there is some sort of current, single electron current which Tong just doesn't even mention it. I mean, 1 electron doesn't mean anything, I guess. That's what I think. 1 electron doesn't mean anything. Okay. So we start. Okay, we've discussed, we have applied to metal insulators, we've seen some things of how to fill the states according to Pauli's exclusion principle, and we also saw that the multi-particle Hilbert space in case of 2 valency is equals to 2 valency is just a single state. It's a band insulator. Okay, then we will start nearly free electrons. Okay, tight binding model and extreme carbon related physics in which space is discrete. Okay, this I will start more